Greetings from California. My name is Tsai. I'm a faculty member at Harvey Mudd College in Claremont, California. The problem that I'd like to talk about today is trying to link two of the largest music datasets, Lakh and IMSLP. Lakh is the largest dataset of MIDI data. It contains 176,000 unique MIDI files scraped from various websites. IMSLP is the largest dataset of sheet music. It contains about 500,000 sheet music scores, mostly of classical music. Now, IMSLP contains a lot of metadata. For each sheet music score, we have information about the composer, the instrumentation, the publisher, when the sheet music was published, any arrangements or transcriptions of the piece, and links to MP3s and CDs containing performances of the piece of music. In contrast, the Lakh dataset has no metadata whatsoever. Even the names of the files are just MD5 checksums. The problem that we try to solve in this paper is linking these two datasets. We would like to de-anonymize files in the Lakh dataset by finding matches in the IMSLP data. This is an extremely large-scale, cross-modal retrieval problem. In this paper, we describe a method for solving this problem, and we present experimental results on a carefully curated set of data where we know what the right answer is. The main idea of this presentation is the following. We can perform large-scale sheet MIDI retrieval by modifying the bootleg score representation for hashing. The bootleg score is a recently proposed feature representation for aligning sheet music and MIDI using dynamic time warping. What we will show in this work is that it is possible to modify the bootleg score representation to make it suitable for hashing. And we will show that it has very good performance for large-scale retrieval. Our proposed approach has three main parts, as you see in this slide. We'll talk about each of these three parts in the next several slides. The first main part is to construct a database of sheet music bootleg scores. The bootleg score is a feature representation of piano sheet music that encodes the position of filled note heads relative to the staff lines. The bootleg score itself is a 62 by n binary matrix, where 62 indicates the total number of possible staff line positions in both the left and right hand staves, and where n indicates the total estimated number of simultaneous note onsets. In this slide, you can see a short section of sheet music and its corresponding bootleg score. Note that the gray staff lines shown here are included just as a visual reference, but are not present in the actual feature representation. I won't go into a lot of details about how to compute the bootleg scores, since that's described in this previous ISMIR paper, but I will give a brief high-level overview. For each sheet music image, we first pre-process the image by converting it to grayscale and resizing the image. And then we detect three different types of objects: filled note heads, staff lines, and bar lines. You'll notice that these three types of objects are all simple geometrical shapes. Filled note heads are approximately circles, and staff lines and bar lines are straight lines. Because these are simple geometrical shapes, it is possible to detect these objects robustly and efficiently using simple classical computer vision techniques. Once we have detected these objects, we can combine the information to construct the bootleg score. The key benefit of using a bootleg score rather than a full optical music recognition pipeline is that the bootleg score is very fast to compute. It can process a high resolution image in under 1 second using just a CPU. Once we have computed the bootleg scores on a set of sheet music images, we would like to construct a database that allows us to perform retrieval efficiently. We do this by first converting each bootleg score column into a fingerprint. Each bootleg score column contains 62 bits of information, so we can represent it very efficiently in memory as a single 64-bit integer. Once we have computed these fingerprint values, we construct a reverse index, where the key is the 64-bit fingerprint value, and the value is a list of all of the instances where this fingerprint value occurs in the database. This includes information about which sheet music it occurs in and where in the bootleg score it occurs. The second main part of our proposed method is to convert the MIDI files into bootleg scores. For each MIDI file, we first extract a list of note onsets and then collapse simultaneous note onsets into events. We then project these simultaneous note events onto the bootleg score. We can map any MIDI note number to a position in the bootleg score using the rules of Western musical notation. Note, however, that there are two different types of ambiguity when doing this mapping. The first type of ambiguity is whether or not a black note on the piano is expressed as a sharp or as a flat. For example, a C-sharp 4 can be expressed as a C-sharp or as a D-flat. And these correspond to two different positions in the sheet music. The way that we handle this type of ambiguity is to construct two completely separate bootleg scores. One bootleg score assumes that all of the black notes on the piano are expressed as sharps, and the other bootleg score assumes that all black notes on the piano are expressed as flats. The second type of ambiguity is whether a note in the middle register is in the right-hand staff or the left-hand staff. For example, a C-sharp 4 could be played by the right hand or the left hand. The way that we handle this type of ambiguity is to place note heads in both the right and the left-hand staves in the bootleg score. You can see in the bottom right corner of this slide both versions of the bootleg score for a short section of music. Notice that there are many more notes in the middle register than you see in the sheet music, and this is because, again, all of the notes in the middle register occur in both the left and the right-hand staves. The third main part of our proposed approach is to perform the search. We use both versions of the MIDI bootleg score to perform two different searches, and whichever one yields a higher similarity score, we use that result as our prediction for the matching sheet music. Our search mechanism is the histogram of offsets method proposed in the Shazam algorithm. We perform the search in exactly the same way, except that instead of using the peak pair fingerprints, we use the fingerprints based on the bootleg score representation. The key idea of the histogram of offsets method is that with the true matching item in the database, we expect to see a sequence of matching fingerprints aligned in time. This corresponds to a line of matching fingerprints with a slope of 1. One way that we can quickly detect a line of matching fingerprints is to compute a histogram of offsets. We expect there to be a large spike in the histogram at the bin corresponding to the true offset. We can then use the maximum histogram bin count as a similarity score between the query and that item in the database. We then sort all the items in the database by their similarity scores. In our experiments, we use 200 different MIDI files as our queries, 40 for training, 160 for testing. For each of these MIDI files, we randomly sampled 10 fragments of length L, and we consider different values of L in order to measure the effect of query length on retrieval accuracy. The database contains the 200 sheet music scores corresponding to those MIDI files, and it also contains additional filler scores. In total, the database contains 5,000 sheet music scores, totaling 55,000 pages. Because each query only has exactly one true match in the database, we use mean reciprocal rank as our metric for retrieval accuracy. Mean reciprocal rank ranges from 0 to 1, where 1 corresponds to perfect performance. This figure shows the results of our experimental simulations. You'll notice that the different groups of bars correspond to different database sizes. As the database size increases, we see that the performance of all the systems gets worse and worse. This is not surprising, since as the database size increases, the problem becomes more and more challenging. But a key observation here is to point out that our system seems to scale reasonably well with database size. For example, as the database size increases from 5 to 50 to 500 to 5,000, the mean reciprocal rank changes from 0.96 to 0.93 to 0.90 to 0.84. Because the number of piano sheet music scores in IMSLP is roughly 1 order of magnitude beyond this, we estimate that the performance of our system on the full IMSLP dataset would be somewhere in the range of 0.75 to 0.80 mean reciprocal rank. Within each group of bars, the different colors correspond to different query lengths. Obviously, shorter query lengths will have worse performance than longer query lengths. We can see that as the database size increases, the query length becomes a more and more important factor. As the problem becomes more challenging, we need more and more context information in order to have good performance. Another key observation to note here is that for queries of length 500 and 1,000, the performance is roughly the same as the performance of using the full MIDI file. This is an important observation because in the real scenario, the MIDI and the sheet music may have structural differences due to repeats or jumps. What this means is that we can handle this problem by simply randomly sampling fragments of length 500 or 1,000, and we know that it won't negatively affect retrieval accuracy too much. Another important aspect is runtime. This table compares the runtime of several approaches to aligning sheet music and MIDI. The top section of this table compares the average runtimes for 5 different methods aligning a single page of sheet music to its corresponding MIDI file. And these average runtimes are averaged across several thousand pairs. The second section of the table uses those average runtimes to estimate how long it would take to perform a retrieval on a database containing 55,000 pages. You can see that these runtimes are very long and that the fastest system would take about 14 hours to search the database for a single query. In contrast, the proposed method in this paper takes about 25 seconds to process a single query. So it's much faster than previous approaches. In summary, this paper presents a method for large-scale sheet MIDI retrieval. And the main approach is to modify the bootleg score in a way that makes it suitable for hashing. Thank you very much for your attention, and I hope that you all stay safe in this time.